similar to Euclidean plane, except that to coordinate we call it as that imaginary axis. Okay, so that you can see very striking differences between real and complex valued functions. For example, if I ask you to draw the graph of the function fx equal to x, how will the graph look like? fx equal to x, real valued function. How will it look like? Anyone can tell? Fx equal to x graph. What type of graph is it?
Straight line, sir.
Straight line, sir.
Straight line, right. So straight line passing through origin. Right, very easily you can visualize and you can draw the graph. So straight line passing through origin making an angle 45 degree with x-axis. Now the same thing when we talk about a function of a complex variable. It's f of z equal to z. F is a function from C to C, means complex plane to complex plane. Earlier that was f is a function from R to R, from real line to real line. You could draw the graph, it's a straight line. Now I am just replacing R by C. So now f is a function from C to C and the equation is same, f of z equal to z. Now how will the graph look like? Try to draw this and tell me how that graph looks like. Fz equal to z. Z is a complex variable. Home? Any idea?
So the PPT is not visible. So is it real axis?
Yeah, PPT is not visible. It is from complex plane to complex plane. In PPT it is not there. The function is f from C to C, and the equation of the function is f of z equal to z. What will be the graph? Home?
So straight line passing through origin of complex plane.
Straight line passing through origin of complex plane. So that means it is same as fx equal to x. You just think how did you draw that graph in case of fx equal to x? Means when we learn initially, I think in class 7 or 8, they give us a set of points, or one for x, one for fx, y. Then we plot those points, coordinates in the graph and then join them. Then we get a straight line. So in that way, you could draw that graph fx equal to x, like for 0, x equal to 0, fx is 0, x equal to 1, fx is equal to 1. So you have got 2 points. Now f of x equal to minus 1, fx also minus 1. If you join these 3 points, you are getting that straight line. Similarly, if you to replicate this process for complex plane, f of z equal to z, now what will be the graph? So you have to take 1 point in the domain, 1 point in the codomain. Any idea?
Sir, can you please repeat once again? I was not able to hear the question.
Question is f of z equal to z. Z is a complex variable. What will be graph? its graph. For fx equal to x, you can draw easily. It's a straight line.
Yes, sir.
So what will be the graph in this case? So you see, if you take that point, suppose one point in the domain you are taking 1 plus I, its output will 1 plus I. 1 plus I, 1 plus I. How will you put it in the graph? Like 1, 1, 2, 2, 0, 0. All these things you can very easily put in the graph and join these points. You get equal to x. For complex plane, how will you do this? Here you see that when the function is from R to R is one dimensional. Yeah.
Sir, we have to plot it on the Argand plane.
Yes. In the Argand plane, domain will be one Argand plane. Its codomain will also be another Argand plane. When the function is from R to R is one dimensional. Input is one dimensional. Output is also one dimensional. So together, is two dimensional. So we could draw, we could visualize it. But in case of function of complex variable, although the equation is same, f z equal to z, but now the function is from C to C. Yes, domain is two-dimensional. Means input is two-dimensional and output is also going to two-dimension. Output is going to C. That's why when you combine them together, the four-dimensional. That's why you cannot draw it because we live in three-dimensional world. So dimension and three we cannot visualize. We visualize one dimension, two dimension, up to three dimension we can visualize, not four dimension. That's why this graph only simple, just the replication of that real function fx equal to x, but still we are unable to draw it. We will not actually be able to do it because input will come from two dimension, output will again be going to two dimension. So put the graph, you to combine them together. That's why it's not possible to draw the graph this way. So these are the differences, basic differences. No complex function graph we can draw or visualize. There are some ways if you put in this softwares like MATLAB, etc. They can give you some idea, but still, since it is four-dimensional, it cannot give you exactly that graph because it will be always four-dimensional. These are the striking differences. So many other differences we will see. So that visualization will not work in case of complex variable, like we could do very easily for real functions. But the process is same. We are replicating the process of differentiation, integration, continuity, etc. But still there are some major differences. So see the definition of continuity, differentiability, etc. Hope you have studied something and you could read this book I could not share it because of its large size. I am writing the name. It's by Skam's Outlines of Complex Variables by Spicer. You find it soft copy or it's available for purchase also. This book you study, you will find all the basic things required for this unit and nicely explained together with lots of solved problems. It's available for free download also. I'm sure you can download that. Try to read this book. Now let us see another example. This one we have seen. I think that okay, some problems we have seen. Let's discuss another example. prove that f of z equal to REZ. REZ means real part of z. The slides are visible? Slide is visible or not?
Yes, sir.
Okay. So REZ means real part of z. Real part of z means if z is x plus y, REZ means fz equal to x. Is nowhere relative. Standard procedures are there by we can determine whether a function is differentiable or not. So f dash z by definition it is same as the case for function of real variable limit h tends to 0 of x plus h plus fx divided by h. That's the definition. Just h is replaced by del z. So if we replace the values here f of z plus del z, it will be x plus del z, only that real part, because the function is fz equal to real part of z. So x plus del x minus fz means again x. They are getting cancelled. Del z means del x plus I del y. So what remains is this del x divided by del x plus I del y. Now we have to prove that it is nowhere analytic, means not differentiable, and not differentiable means this limit does not exist. And by existence of limit we mean that the limit should be unique, independent of the path through which that tends to 0. So you can show that the value of this limit is different for different paths. Now our job is done. So that's what I'm going to do here. I'm going to show that this limit depends on the path. That is, it is not unique. So we approach 0, let delta tends to 0 along the straight line y equal to mx. Since it is the plane, there are infinitely many directions through which we can approach 0. We can approach 0 through x-axis, y-axis, or straight lines of passing through region y equal to mx, or several curves passing through region. Anything will do. So here we are taking one easy choice, y equal to mx, this straight line. We are approaching 0 along this straight line. In that case, del y will become m del x. It is just like taking del on both sides. Del y will be m del x because we are approaching along this line. Therefore, now this definition becomes f dash z equal to limit del z tends to 0 means it will be simply del x tends to 0, because if del x tends to 0, del y also automatically tends to 0. So it's substitute to write del x tends to 0. What remains is this del x weighted by del x plus I del y, but along this straight line del y becomes m del x, m del x. Now this del x, it tends to 0 means it is not equal to 0, therefore it can be cancelled from numerator to denominator. So we have this limit 1 divided by 1 plus im. So you can see that in the limit that m is present. M is present means if you change the slope of the straight line, this limit will also change. So that's why this limit is not unique. It depends on the straight line through which you approach origin. Therefore, this limit does not exist. Therefore, the function is not differentiable. And not differentiable means not analytic at any point. So that is the case. These are some standard techniques while proving a function is not differentiable or not analytic. Usually we take these three paths. These are the easiest of the paths to work with. One is along x-axis. When you move along x-axis, y-axis becomes 0. Other is y along approaching 0 towards y-axis. Then x coordinate becomes 0, and another one is approaching 0 to the straight line y equal to mx. In this case, we have used this one. Previously, we have used x-axis and y-axis. Here we are using y equal to mx. You can also check if you can prove this by using this approaching zero to along x-axis or y-axis not. You can do by that will also be alright. Here we have used y-equal to mx. So unless you read the book and read the theory properly, you will not understand complex variable that, because this visualization is not be possible in this case. What complex derivative means, like derivative of a real valued function gives you the slope of tangent to that curve at that point. But in case of complex variable, no such physical significance is there. In case of real variables, when we integrate, when we find definite integrals, it has a physical interpretation which gives us the area bounded by curve. But when we study complex variables, if we perform definite integral on complex functions of complex variables, it does not have such physical interpretation. One such example I have discussed, that you are unable to draw the graph of a complex valued function because graph is 4-dimensional. But it has lots of application. That's why in the beginning I tell that complex variables are not used for our everyday computations. We nowadays these real numbers are sufficient, but for advanced scientific computations, complex variables are used. Don't think that they don't have any use because we don't directly see them, don't use them in real life for our money transaction or counting. They have other utilities. Mostly they are used for advanced computations. Depending on the situation, complex integration, complex differentiation have different meanings. Let's see another example that fz equal to mod z square is differentiable at z equal to 0. And thus it is nowhere analytic. Here again, same thing. We have used this definition as z equal to this mod z square. So here f of z plus del z square minus f of z divided by del z. So when we take this limit after simplification, we arrive at this expression. And this expression here, the problem is this limit does not exist. This limit is sum of this limit plus this limit plus this limit. This one exists, this one also exists, but this del z bar divided by del z, it does not exist. That's why the entire limit does not exist. So this has been proved here. How this does not exist. If z equal to 0, then f dash 0 equal to 0. But since del z bar divided by del z equal to this, we can, like earlier, that this limit does not exist. I took this part, that del z bar divided by del z is equal to this expression, and when you take limit as del z tends to 0, it does not exist. Like earlier, if you this proof is easy once you approach 0 along x-axis, then y will become 0, then the limit will be 0, this will be 0, so del x by del y, this will be 1. And once you approach 0 towards y-axis, then x will be 0, 0, this 0. What will remain? Minus I divided by plus I, that will be minus 1. So once you are getting the limit plus 1, and again you are getting the limit as minus 1. That's why this limit does not exist. The entire limit does not exist. I have not written properly here. You do this calculation. Up to you will arrive, and finally you show that this limit does not exist by earlier techniques. Okay, so that's why you have to read from the beginning how and learn the techniques, how to prove something is not differentiable. And while proving something is not differentiable, it will boil down to showing that the limit does not exist. And how to show limit does not exist, we have discussed several procedures. you can approach 0 towards several directions. One is along, and three common directions we use, these are easier to use. One is along x-axis, other is along y-axis, and another is, if these two do not work, then you go for y equal to mx. If none of them work, then we go further towards some curves, but most of the cases they will work. So here that will work once you approach 0 along x-axis, again you approach 0 along y-axis, and this limit, you can show that this limit is not, you are getting 1 and minus 1 as the limit. This is not defined. Here another question, find the points where f of z equal to r is z is differentiable. Where is it analytic? This one already we have seen that f dash z equal to this limit along, if we move along y equal to mx, then we arrive at this limit, which is not unique. So if dash z was any arbitrary point, it is not differentiable at any point. The answer is it is not differentiable at any point, and therefore there is no question of this in analytic. I don't know whether you have studied or not. There is a difference between analyticity and differentiability. Analyticity at a point means that should be differentiable at that point, also at all points in a neighborhood of that point. At all points, it should be differentiable, not only at one point. A function may be differentiable at one point, but it may not be analytic there if it is not analytic at a very nearby point. So this criteria has to be satisfied. So analytic means differentiable, but differentiable although it not mean analytic. This question was about finding whether the function is differentiable or not and whether it is analytic or not. So firstly, we have seen that it is not defined at any point, so automatically we can conclude that it is not analytic as well. If it is not differentiable, it cannot be analytic. And if it is analytic, it must be differentiable. But converse is not true. If it is differentiable, still it may not be analytic at that point. So we need those differences properly. That the difference between differentiable at a point and analytic at a point. As you would understand the difference right now, it will not be clear to you. So you read that book, any other book you will find. In this book, nicely it is explained what are the differences. Several examples. Next is question, give an example to show that existence of Cauchy-Riemann equations at a point does not imply the differentiability of the function at that point. Cauchy-Riemann equations we discussed in the beginning. Here, Cauchy-Riemann equations. Cauchy-Riemann equations are ux equal to vy, uy equal to vx. But you read the beginning that it is necessary condition, necessary, not sufficient. What it means that if a function is analytic or differentiable at a point, then these equations must be satisfied. But if these equations are satisfied, it does not mean that the function is differentiable at that. One side is true only, that's why it is necessary, not sufficient. Necessary and sufficient means if and only if both sides true. Necessary means only one side is true. In this case, if a function is differentiable, then these conditions will be satisfied, but converse is not true. This condition is satisfied, but still the function may not be differentiable. That's what this example is saying. This say that you give example to show that Cauchy-Riemann equations are satisfied at a point, but still the function is not differentiable at that point. You have to generate an example. So this is one standard example to show this. Fz equal to square root of mod xy. This function we have taken. Suddenly it will not come to you. Suddenly it will not come to me. I have done this already, so I have written. So you also have to know some examples of this type, where one side is true, converse is not true. So if we take this function, let us call it u plus I views, and that real part and imaginary parts are required to apply Cauchy-Riemann equations. Because we need ux equal to vy, uy equal to minus vx. So we have identified what is the real part and what is the imaginary part. So u real part is this, only real part, this function, this imaginary part is 0. Obviously you can check. So let us see if Cauchy-Riemann equations are satisfied at some point. Let us take origin 0, 0 or 0 plus I0. So at this point we need to check whether Cauchy-Riemann equation is satisfied. Cauchy-Riemann equation means ux, partial derivative of u with respect to x. This is the definition. Only this x coordinate is changing, y coordinate remains unchanged, same. So when we take the limit, we get 0. So u is 0 at the origin. Similarly, you check vy. Vy, only that y coordinate will change because we are talking about this partial derivative with respect to y. So only y coordinate change, 0. Similarly, that same definition will apply Vx, Vy, you have to find. And you will see all of them are 0. Therefore, Cauchy-Riemann equations are satisfied. It is x equal to Vy. In fact, all are 0, so Uy is also equal to minus Vx. 0 equal to minus 0. Therefore, Cauchy-Riemann equations are satisfied at the origin. So, one part we have shown that CR equation satisfied, but we have to show it is still not differentiable at that point. That is, only one side of that necessary condition is on the other side. It is CR equation satisfied, but the function is not differentiable. So at the origin, let us apply the usual definition of differentiability. Del z tends to 0, f of 0 plus del z minus f of 0 by del z. So this limit 0 plus del z means del z minus 0 divided by this. Our function was fz equal to square root of mod x. So f of del z will be square root of del x del y divided by del z. Del z tends to 0 means del x plus I del y. Now we have here what we are doing, we are approaching 0 along straight line y equal to mx. We are approaching 0 along the straight line y equal to mx. So in this case, del y will be I mx. That I have not written here. You have to write this in the beginning. That let del z tends to 0 along y equal to mx. The path we have to mention. Likely del y will be I mx. So this I can be taken common and taken outside. So after simplification, you will arrive at this del x will also get cancelled. Here you have square root of del x. It will become del x. So del x will get cancelled. Finally, you will have square root of mod m divided by 1 plus im. Therefore, this is not unique because it is again dependent on the path y equal to mx. I have not written here, I'm telling again, so you write in the beginning that del z tends to 0 along y equal to mx. Then only we are arriving at this expression. It depends on m, so if you change m, then the value of the limit also changes. So therefore this limit is not unique, therefore it is not differentiable at origin. Did you understand that? Sunil,
Yes, sir.
समझ में आ रहा है या कोई डाउट है?
Yes, sir. Understanding it.
Okay. Try to understand. You have to understand properly. You have to read the book also and solve some more problems. And here also, whatever problem I have given from the beginning, try to solve them in pen and paper and understand the steps one after another, how they are coming and what you are actually doing. Main thing is that when you have to show that a function is not differentiable, you have to show that you have to apply definition so that this limit is not unique. Taking whichever path is convenient for you. Some other problems are also given here. Try to understand them. You can ask me anytime if you have any doubt. Next, let us see another example. Let f equal to iv, where u is the real part of the function. This is the real part. This is the imaginary. The question is, why is f differentiable? And does there exists an entire function g whose real part is u? Is so given example. There exists an entire function h whose imaginary part is b. So given example. First, let us see this first question. Where is f differentiable? Can you find it? A function is given to you. F equal to u plus iv. So u is given, v is given. Means real and imaginary parts are given. Can you tell at which points this function is differentiable? To determine differentiability, we have Cauchy-Riemann equations. So if it is differentiable, the Cauchy-Riemann equations must be satisfied by this equation. So tell me now at which points Cauchy-Riemann equations are satisfied. U is given, V is given. So you calculate Ux, calculate Vy, and tell me at which points Ux equal to Vy and Ui equal to minus Vx. Ux will be what? This is U. Ux will be what? Ux means partial derivative of u with respect to x. Vikiran, Ux will be tell me the expression for Ux.
2x plus 2y.
Ux will be Ux means partial derivative of this with respect to x. इसका partial derivative x square का partial derivative with respect to x क्या है?
2x.
2x फिर इसका क्या होगा? 2xy. इसका partial derivative with respect to x. y तो constant हो जाएगा. Will be constant. So it will be 2 y only. Derivative of x is 1. And the derivative of this will be 0. Partial derivative, this is constant. So ux will be twice x plus twice y. Okay, so this ux equal to twice x plus twice y. Similarly, find vy. Vy is partial derivative of this with respect to y. This becomes 0. This means minus 2x. Here you have minus 2y. Okay. ux and so for Cauchy-Riemann equations to be satisfied, this should be equal to this. Means ux should be equal to vy. That means 2x plus 2y should be equal to minus 2x minus 2y. That means it should imply x plus y equal to 0. This first Cauchy-Riemann equation is satisfied on the straight line x equal to minus y. Next, you have to show that other part of Cauchy-Riemann equation also should be satisfied. That means you have to calculate uy vx. So uy should be equal to this is uy, this is vx. Now uy equal to minus vx if and only if x equal to 0, y equal to 0. Means again x, this gives you x plus y equal to 0. Now both these equations are satisfied together if x equal to and y equal to 0. Because otherwise this equation is not satisfied. So 2y to y gets cancelled, means twice x equal to 0. This gives x equal to 0. X equal to 0 from this equation we have y equal to 0. After solving these two equations, we have only this point, x equal to 0, y equal to 0. Therefore, this function has a chance of being differentiable only at one point, where Cauchy-Riemann equations are satisfied, and this is the only point where CR equations are satisfied, which is origin. So, differentiable only at origin. So, differentiable at origin if Cauchy-Riemann equations are satisfied plus first partial derivatives are continuous. Here first partial derivative is this. All are linear functions in x and y. They are and they are obviously continuous. That's why it is differentiable at this point. How we determined the differentiability at a point? If a function is differentiable at a point, CR equations must be satisfied. So we have checked at which points CR equations can be satisfied. We have found that there is only one point where this CR equation is satisfied. Therefore, it is differentiable only at that point, at no other point. Next part, does there exist an entire function g whose real part is u? Entire function means a function which is differentiable at all points of its domain in C. For that, one result is required unique function. Yeah, harmonic function definition is written here. Harmonic function, a function phi of x. Here it means it's a function of two variables x. It's a real valued function. A real valued function is called harmonic if this equation is satisfied. Del 2 phi del x2 plus 2 phi del y2. And second partial derivative of that function with respect to each of the variables. And their sum is equal to 0. If condition is satisfied, that function is called harmonic. The null result is there. in connection with functions of complex variables. Prove that real and imaginary parts of an analytic function are harmonic. Real and imaginary parts of an function are harmonic. That is, if a function is harmonic, then its real and imaginary parts. If a function is analytic, if a function is complex valued function is analytic, then real and imaginary parts must be harmonic. As the proof is very simple, that fz equal to u plus iv. Since it is analytic, analytic means differentiable also. So CR equations will be satisfied. So ux equal to vy and uy equal to minus vx. These two will be satisfied. Now you have to prove that u is harmonic, v is harmonic. Means v both should satisfy this equation. That means you need to take the second partial derivative with respect to each of the variables. So ux equal to vy, therefore uxx is equal to vxy. Similarly, uy equal to minus vx, so uyy equal to minus vxy. Therefore, if you take their sum, uxx plus uyy, they are getting cancelled and you are having 0. So that means u satisfies this equation. Similarly, you can prove that v also satisfies this equation. This completes the proof. So what it says that if a function is analytic, then its real part is harmonic and its imaginary part is also harmonic. So that you need to prove the problem. We're talking about what this question says, that does there exist an entire function? Entire function means differentiable everywhere, means analytic everywhere. G, whose real part is u. What you need to check, that if it is not harmonic, then it cannot be the real part of any analytic function. So that's what we have shown. We have found u is given to us. So you have found ux, and ux is 2x plus 2y. So xx means again you take the partial derivative with respect to x. So this 2 derivative x is 1, and this is stated as constant partial derivative. So this becomes 0. You have xx equal to 2. Similarly, u equal to this, so uyy is also 2. So you take their sum, uxx plus uyy, it becomes 4. 2 plus 2, 4, which is not equal to 0. Therefore, u is not harmonic. If u is not harmonic, it cannot be the real part of any analytic function. Entire function also means analytic function. It is differentiable everywhere. Okay, so u is not harmonic. If a function that you remember from that result we just discussed regarding harmonic function, that if a function is analytic, then its real part must be harmonic, imaginary part must be harmonic. Here we've seen that real part is not harmonic, therefore it cannot be the real part of any analytic function. Next, similar question for v, that imagine. Here what we see that vx equal to 2, vyy equal to 2. So vxx plus vyy becomes equal to 0. That means v is harmonic. Oh yes, since it is harmonic, it can be the imaginary part of some function. If so, if your answer is here, then give an example. So we have seen that the function is harmonic, therefore such a function may exist. Now if it exists, you have to find that function. It is already given to you, you have to find that function. That means the real part you need to find. From these equations we will find. Our aim is to find u. So ux equal to minus 2x minus 2y. Ux will be equal to vy, or vy is given to us, so vy equal to this Since the function is analytic, so uy should be equal to ux. Ux equal to this. Now we integrate with this expression with respect to x. If we integrate with respect to x, we will have simply u on the left hand side, and the right hand side we have minus 2 into x square by 2. Here we are integrating with respect to x, treating y as constant. So this will be minus 2xy plus, in case of usual integration, we give an arbitrary constant, but when we are integrating partially with respect to x by treating y as constant, then instead of arbitrary constant, we have to write a function of y. Well, if we differentiate this with respect to x, this will become 0. So it may be a constant, but and also it may be a function of y. So we are writing the general case, a function of y. So we obtain this expression. Again, the other part, ui also should be equal to minus bx. B is given to us, so minus bx will be this. So now f1 dash y is equal to minus equal to 2y after simplification. Now integrating this, we obtain this y square plus c. Okay, so f1 we have got. Initially we have obtained an expression for y. Then second CR equation gives us this. From this we find out what this f1y is. F1y is y square plus c. Therefore we have found the real part, u equal to this. Therefore our function is u plus ib. B is that given one. I can understand right now you are not understanding exactly what the solution is, so you need to read carefully all these things, you will understand. Okay, and if you have any doubts, you ask me anytime. The main thing is to know what is a differentiable function, what is an analytic function, and what are their differences. Also, harmonic function, what is a harmonic function, what is its connection with analytic function. This connection is given by that result, that if a function is its real and imaginary parts must be harmonic. So this connections, if you understand, then this will be there. Then there is another theorem called Liouville's theorem. So function of complex variables people find difficult because that visualization does not work here. In real analysis, all the things we can visualize, we can give physical interpretations, so we can understand what it actually means, what is the meaning of derivative, what is the meaning of integration, but say does not happen with complex functions of complex variable. One Liouville's theorem is there. It says that a non-constant entire function cannot be bounded. A non-constant entire function cannot be bounded. A function, like I told earlier, entire function means a function which is differentiable at every point. Can you give an example of such a function which is differentiable at every point? Anton, can you give example of a function which is differentiable everywhere? Anton. All have left or what?
No, sir.
So give me an example of a function which is differentiable. Always differentiable.
Sir, can it be sine function?
Right, sine, because if you differentiate sine, always you get cos. If you differentiate cos, you always get minus sine. If it can be also e to the power x, if you differentiate it, always you get e to the power x. So these functions are everywhere differentiable. Okay. Now, when we talk about real sine function, sine x, x is a real variable. Then that function is bounded or unbounded. Bounded means it has an upper limit and lower limit. It's range.
Yes, sir, it's bounded.
Does it have an bounded by -1 and +1, isn't it?
Yes, sir.
Because we know that value of sine lies between -1 plus. Similarly for cos. What about e to the power x? Is it bounded? E to the power x,
No, sir.
initial function, is not bounded because as you increase the value of x, that value of e to the power x also increases arbitrarily. So you cannot find an upper limit. It can be always bigger than whatever you think of. On the graph also it is clear that it is going upwards only as you move towards right. So that is unbounded. Now what Liouville's theorem states, this also gives you a striking difference between these functions of real variables and functions of complex variable. This theorem says that if a function is not constant and if it is entire means if it is differentiable everywhere, then it is not bounded. Now, when we think of sin x function is everywhere differentiable. So it is an entire function, and sin x is not a constant function also. Isn't it? Sin x is not a constant function, but it is bounded. But in case of complex variable, it says that a non-constant entire function cannot be bounded. If a function is not constant and if it is differentiable everywhere, it cannot be bounded. So sin z, when you replace that variable x by z, complex variable z, it becomes complex sine function. Now it cannot be bounded, means its modulus or magnitude can be arbitrarily large. It does not lie between -1 and +1 like sine function. These are some major differences between real functions and complex function. Real sine function, cos functions are bounded. Complex sine function, cos functions are unbounded. Their modulus can be arbitrarily large. Okay. So that's what I have written difference between sin x, cos x in C and R. Now sufficient condition for analyticity or differentiability. Chiriman case we have seen earlier. One example also we have seen that a function for a function equations may be satisfied, but still it may not be differentiable. But when the other side will also be true, Cauchy-Riemann equation plus something has to be there so that the function is differentiable. That plus something is given by this result. A sufficient condition for fz equal to u plus iv to be analytic in a region R is that its partial derivatives ux, uy, vx, vy exist. They are continuous and satisfy Cauchy-Riemann equations. So Cauchy-Riemann equations plus these partial derivatives are continuous gives you analyticity or differentiability. Only Cauchy-Riemann equations don't give you that differentiability criteria, but Cauchy-Riemann equations satisfied plus these partial derivatives are continuous will imply that the function is differentiable or analytic at that point. So we have discussed many things. You need to understand also, so you read them carefully. I have told you the book also you'll find online in several websites, free. It's freely downloadable. Read that, or you can read other books also, whatever is convenient for you. Okay, so this is all about complex differentiation. Next class we'll discuss complex integration. Your syllabus will be in same syllabus. We'll keep 2 units only. It will be completed within a few classes, 2-3 more classes. So that's why we are not taking 2 classes weekly. 1 class per week will be sufficient. So tomorrow's class will not be held. So I'm taking only 1 class per week. That will be sufficient. To try to understand these things, analyticity, differentiability, what is harmonic function, what is its connection with analytic function, all this. Complex analysis understanding will take some time. You have to give some effort. Of course, if you want to understand, if you want to pass the exam, that will not be difficult, particularly in this situation. All are passing. But if you want to think about it, that point matters the most. Try to understand what you are doing, why you are doing. Passing that will be a big issue. So it will be all for today. As I told, I will take 1 class per week. That will be sufficient. Let me take that. Abhijit.